Hello everyone, welcome to our project overview. House space prediction using linear regression. The whole project is done by a group of three people, Nitul Singha, Shubhankar Roy and Sujoy Das. We all are doing our MSc in statistics from University of Kalyani. Project description. The house space prediction with KC house data under guidance of Dr. Ganesh. The whole presentation is created and presented by me. We will be using data from a Kaggle dataset. You can easily get it through this link. Okay, let me introduce with the feature columns of our data. ID, date, price, bedrooms, bathrooms, square foot living, square foot lot, floor, waterfront, view, condition, grade. To know more about these features, pause the video and read carefully. And here also square foot above, square foot basement, air built, air renovated, zip code, latitude, longitude, square foot living 15 and square foot lot 15. Again here, to know more about this feature, pause the video and read carefully. Okay, let me introduce the units of our feature variables. Price rupees, bedrooms numbers, bathrooms numbers, square foot living feet, square foot lot feet, floor number, waterfront binary, view binary, condition number, grade number, square foot above feet, square foot basement feet, air built air, air renovated air, zip code number, latitude number, longitude number, square foot living 15 feet, square foot lot 15 feet. Now check the head of our dataset. Now the most important part of a project. What is our project objective? Here our objective of our project is to predict the price of a house on the basis of all other explanatory or feature variables. Wait, before getting deep into this project, take a brief look on linear regression. It is a way of finding a relationship between a single continuous called dependent or target variable and one or more other variables called independent variables. Assumptions. Linearity and additivity of the relationship between dependent and independent variable. Statistically, independence of the error. Homostaticity of error. Normality of the error distribution. Variable type. Linear regression requires the dependent variable to be continuous, that is numerical values, and independent variables can be continuous as well as categorical. Simple versus multiple linear regression. Linear regression can be simple linear regression when you have only one independent variable, whereas multiple linear regression when you will have more than one independent variable. And regression equation, which is familiar to us, y equal to alpha plus beta 1 x1 plus beta 2 x2 plus dot 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 beta n xn plus epsilon. Interpretation. Alpha is the intercept, the expected mean value of the dependent variable y when all the independent variable xj's are equal to 0. Beta j is the slope. It represents the amount by which dependent variable y changes if we change xj by 1 unit, keeping other variable constant. Epsilon is the error variable. Residual. The difference between an observed value of the dependent variable and the value of the dependent variable predicted from the regression line. Linear regression is based on the least square estimation, which says regression coefficient should be chosen in such a way that it minimizes the sum of square distance of each observed response to its fitted value. Now, one question may arise in your mind that let's start. Check the info of our dataset. What is the best rule for regression analysis? Look, there is no hard and fast rule for doing regression analysis. We have already seen that there is no missing a good model in the dataset along the following which is too good. Step 1. Now, we look into the correlation dependent of the explanatory variables with our target variables. Step 2. Univariate analysis. Let's visualize the correlation values or outlier detection for better understanding. Step 4. Feature engineering. Through this heat map, I have noticed that some of our explanatory variables are highly correlated between themselves. Such situations strongly unexpected and may cause a multicollinearity in our future model. However, we will not take any action to Step 7. Variable reduction. Remove a variable is so easy, but not a solution. Step 8. Model building. It may cause of losing information. Step 9. Model evaluation. Along with those variables, we observe that the variable Step ID 10. Is irrelevant model validation for our purpose of model building. As well, and we have convert the column year renovated and square foot basement into binary form. Year renovated is equals to 0 if the house is not repaired, equals to 1 if the house is repaired. Square foot basement equals to 0 if there is no basement, equals to 1 if there is a basement. And we create a new variable houses named age h, which gives us the age of the house when it has sold. For the task, we just simply extract the year from the date column and subtract by the column year built. Now we look for the outliers if any. From those two pictures, we can clearly see the existence of outliers in our data, which is so expected from this kind of data. Now we will check for the multicollinearity among the explanatory variables. As we can see from the VI values, the square foot living and square foot above has high VI value. So we will take action on those two variables. Now we will check for the multicollinearity among the explanatory variables. As we can see from the VI values, the square foot living and square foot above has high VI value. So we will take action on those two variables. Here we have clearly seen that the model have strong multicollinearity between two variables square foot living and square foot above. In this situation, instead of dropping any one of these two, we make a new variable square foot equals to 1 by 2 into square foot living plus square foot above. Then simply drop both of these two square foot living and square foot above. Now we will check for the influential point in the dataset, if any. From this picture, we can see there exists influential point in the data. Now simply identify and eliminate those data from our dataset. Now fit a linear model with all the updated variables. As we can see, the adjusted R-square values is increases to 0.738. This is quite acceptable. Here we run stepwise forward regression to find the best fit model. To know what actually forward selection is, pause the video and read carefully. Here we arrived at this model. The adjusted R-square of this model increases to 0.7481. Now we check the assumptions of the model. Normal QQ plot. From this plot we can see as the observation do not fall upon the reference line, so the normality may not hold. The residual versus fitted plot. There is a random pattern in residual versus fitted plot, but we see that the horizontal line is near to 0, so we can say that the linearity holds for our dataset. From residual versus leverage plot, we can say we see that there is a high leverage point in our dataset. And second, but all the observations are under Cook distance line, so there is no presence of influence point in our dataset. The scale location. The random pattern reference line does not follow any pattern, hence homoscedasticity holds. Let's talk about the predicted values. From this small table, we can make few comparisons of actual values with our model predicted values. And by the predicted price versus actual price plot, we can see our model is well fitted. Conclusion. Here the final model in our hand, which is shown below. The model RMSE is 1,51,589.9. AIC value is 981.4906. Adjusted R-square value is 0.7481. One can easily use this model to predict the price of a house based on the exploratory variables we have mentioned. Here the references are shown below, and all the work of our project is done in Python and R programming language. And special thanks to Dr. Ganesh for all the support. Thank you everyone. Hope you enjoyed our project overview.